Okay, so welcome to the second talk of this session. So we have Sathyawageeswar Subramanian from the University of Warwick, and he's going to tell us about sublinear quantum algorithms for estimating the Neumann entropy. So Sathyawageeswar, the stage is now yours.
Thanks, May. So this is joint work with Tom Gore and Min-Hsiu Hsieh. And I'll be talking about work that was recently out on the archive in this paper that you can find at this link here. So what is the main theme of my talk going to be? In the classical setting, in classical distributional property testing, it's been known for about 20 years now, since groundbreaking work of Batu et al. In 2002, that you can estimate the Shannon entropy of distributions, of an unknown distribution, up to a multiplicative precision gamma with a complexity that's sublinear in the alphabet size. So in a sense, that's sublinear in the size of the input. So the question that got us started on this work is it possible to do something similar for quantum states? In particular, can we estimate the von Neumann entropy of an unknown quantum state with complexity that's sublinear in the dimension of the state? So what I'm going to tell you about in this talk is that yes, we can do this, given that we have coherent access to the state. And I'll define what coherent access is in a bit. And along the way, we'll also see that we can get a quadratic speedup for over classical algorithms for estimating the Shannon entropy of classical distributions in all known quantum input models. And we'll also show some non-trivial lower bounds on the problem of entropy estimation. Okay, so the talk is structured like this. I'll quickly go over some background and definitions. We'll see some related work, and then depending on how much time there is, I'll go into some of the details of the techniques that we use in our proofs, and also quickly mention what the lower bounds are that we prove. Okay, so to get definitions out of the way first, the Shannon entropy of a distribution on n items is defined in the standard way. So it's the sum over pi times log of pi with a negative sign in front. And the von Neumann entropy of mixed quantum states, represented by density matrices, is defined by negative of the trace of rho log rho. So this is very much analogous to the classical case. And in particular, the von Neumann entropy is exactly equal to the Shannon entropy of the spectrum of the state rho, of the density matrix rho. Next, additive versus multiplicative estimates. So additive estimation is something that everyone knows about commonly. It's something that's more common in the algorithms literature. So an additive estimate x tilde of some unknown quantity x to precision epsilon should satisfy this property. It must lie in between the true value minus epsilon and true value plus epsilon. This also implies, so it's worth noting that this also implies that once an algorithm tells you an estimate x tilde of the unknown quantity, if it has an additive guarantee, then that will mean that the true value, the true unknown value, is going to lie in between x tilde minus epsilon and x tilde plus epsilon. So multiplicative estimates are something similar. So if you have a factor gamma that's larger than 1, then a multiplicative estimate x tilde of x has to lie in between x over gamma and gamma times x. So for example, if gamma was equal to 2, then what you want here is that x tilde has to lie in between half the true value and twice the true value. And once again, as with the additive case, if an algorithm tells you that x tilde with high confidence is a multiplicative estimate of x, then x is going to lie in between, the true value is going to lie in between x tilde over gamma and gamma times x tilde. Okay, so why are we interested in multiplicative estimates in the first place? That's because in a sense, they're very general. So one way in which they're general is that for quantities on which we know an upper bound a priori, such as the entropy. So we know that the entropy of a system in n dimensions, of a quantum system in n dimensions, or a classical distribution on an alphabet of size n, is bounded above by log n. This allows us to manipulate the multiplicative estimate to get an additive estimate, to recover an additive estimate at the end. So if we set the multiplicative precision to what you can see here, 1 plus epsilon over log n, then the series of inequalities below will show you that you can recover an additive estimate. And in particular, at the end, the complexity overhead that you incur in doing this is, so this is not something I'll talk about in this talk, but it's in our paper. And you recover the same complexity as you would if you started out by setting up an additive estimation algorithm. Another reason why multiplicative estimates are interesting is that they have many applications. So sometimes we're interested in knowing whether a quantity, say the entropy, is just large or small. So given two thresholds, H1 and H2, we may want to know if the entropy is larger than the larger threshold or smaller than the smaller threshold. And we can do this profitably by estimating the unknown entropy to within a multiplicative factor, gamma, that's defined by the square root of the ratio of these thresholds. So multiplicative estimates are useful in gap problems, and more generally, multiplicative estimates are useful for a variety of property testing problems. In particular, because we're talking about distributions and states here, they're useful for distributional property testing problems. Okay, so how are our algorithms going to access the input? This is obviously one of the most important parts of defining quantum algorithms or algorithms in general. So there are four popular input models that have received attention in the quantum literature. Alexander Belob's has a paper from 2019 where he discusses these four input models in a fair bit of detail. So the first model that was ever used in quantum algorithms for testing properties of classical distributions is called the frequency vector model. So in this model, we have a string of length m, where every index contains an instance of a label from the set of labels 1 up to n. And this string is promised to have the property that for every I that's a label, the probability p of I is exactly equal to 1 over n times the number of times the index I or the label I occurs in that string. So as you can see in the example in red here, the label 1 occurs 3 out of 6 times. So P1 is equal to 3 over 6, which is a half. And the label 2 occurs 2 out of 6 times. So its probability is P2 equals 1/3 and so on. We won't be using this model too much except to prove lower bounds in this work. Another popular input model for quantum algorithms that access classical distributions is the quantum samples model. So in this model, you have access to a unitary that prepares this state P on the right-hand side of equation 1, where P has the property that measuring it in a computational basis essentially has the same effect as drawing a sample from the distribution P. This is known to be a very powerful input model, and it's been used widely in quantum learning theory, in particular on a theory of quantum path learning and agnostic learning. And the actual input model that we're more interested in this work is called the purified quantum query access model. So what this model assumes is access to a unitary U row, which prepares a purification of an unknown density matrix row. So equation 2, the right-hand side, the middle portion of equation 2 is the purification of the state row, such that tracing out the second register gives you a copy of row. And psi and phi are sets of orthonormal vectors on a system and an ancillary register. This model is very general in the sense that it can capture both pure and mixed quantum states, and it can also capture classical probability distributions, which are just diagonal density matrices in the computational basis. And the generality of this model can also be looked at from another point of view, which is that any input, the other two input models, the quantum pure samples input model, as well as the frequency vector input model, can emulate the purified access model in the sense that given a frequency vector or a samples oracle, you can construct a purified quantum query access oracle for that same input with constant overhead. Okay, so there's been a lot of work on entropy estimation in the last 2 decades in both the classical and quantum algorithms literature. So additive estimation has essentially been tightly characterized. So the classical sample complexity of estimating the Shannon entropy to additive precision is essentially linear. So it's n over log n, and it depends inversely on the precision that you want. The quantum query complexity of this problem was shown to be quadratically better than the classical complexity. So it's square root of n. This was recently proved by Gillian and Lee in 2019. And they also used the same input model that I described on the previous page, the purified query access model. The multiplicative estimation of entropy has been studied for 20 years as well. And the upper bound, the upper bound that essentially turned out to be tight later was shown in 2002 by Batu et al. And it's essentially n to the 1 over gamma squared. And essentially matching lower bound was proved in 2011 by Paul Wallin. So in this work, we show that for the Shannon entropy, quantum query algorithms that have access to the input via purified access oracles get a quadratic speedup over classical algorithms. We also show a lower bound of n to the 1 over 3 gamma squared by reducing the collision problem to entropy estimation. So it's worth noting that we assume here, both in the classical and the quantum case, that for gamma multiplicative estimation, the entropy of the input has to be larger. It has to be bounded away from 0. And in particular, we assume that it's at least gamma over eta. And as you can see, this parameter eta appears in the complexity as well. And this stems from the fact that no polyquery algorithm, classical or quantum, can multiplicatively estimate the entropy of distributions that have arbitrarily low entropy. And we will also see this a little bit later in the lower bounds section. Okay, so for the von Neumann entropy, as far as we know, there haven't been any studies on estimating it to multiplicative precision before ours. For the additive estimation of von Neumann entropy, Acharya et al. Showed that if you had samples, if you had copies of the state rho, then the complexity is essentially quadratic in the dimension. And this also matches the complexity of doing full quantum tomography on the state. Gillian and Lee show that if you have purified quantum query access, then you can output epsilon additive estimates of the von Neumann entropy in essentially linear complexity. What we show in this work is that you can estimate von Neumann entropy to multiplicative precision, gamma, with essentially n to the 1 over gamma squared queries to the purified access oracle. And the important part here is that because gamma is larger than 1, this complexity is sublinear. It's sublinear in the dimension of the state n. And because we know that quantum states can have very, very large dimension, in particular, the dimension scales exponentially in the number of constituent particles, sublinear complexities are quite interesting and potentially useful. So, and as I mentioned before, because classical distributions are essentially diagonal quantum states, the lower bound from the previous slide follows over. So we have an n to the 1 over gamma squared upper bound on the gamma multiplicative estimation of the von Neumann entropy, and an n to the 1 over 3 gamma squared lower bound on quantum algorithms that output multiplicative estimates of the von Neumann entropy. Okay, so how do we actually achieve this? In the first place, how does the classical algorithm achieve a sublinear complexity? The idea is something that's by now quite pervasive in the distributional property testing literature. We first divide the set of labels into quote unquote big and small elements with respect to some choice of threshold. So we have a set B of big labels or heavy labels, which have large probability mass. And we have a set S of small labels that have low probability mass. And because the Shannon entropy is linear in a sense, you can express the entropy of the whole distribution as the sum of the contributions of the entropy of the big elements and the small elements. And the strategy of both the classical and our quantum algorithm is to estimate these contributions separately. So we deal with the heavy elements separately, and we deal with the light elements separately. And usually it's the light elements that are hard to deal with, because when you draw, on any distribution, when you draw samples from it, you're unlikely to see elements that have low mass. So you need to draw more and more samples if you want to see elements with lower and lower mass. And in the end, the goal is going to be to make the threshold as large as possible, because the complexity will depend exactly on the inverse of the threshold. And in particular, eventually we'll choose it to scale as n to the minus 1 over gamma squared, where gamma is the target precision for multiplicative approximation. And the key lemma, the key property of lightweight elements that allows us to use the strategy on the previous slide is what's encoded in this lemma here. So if you assume that the set of lightweight labels has a total weight W, then it turns out that you can tightly bound the contribution that the lightweight elements make to the entropy, both from above and below. In particular, if we choose the threshold to be of this form of the form n to the minus 1 over gamma squared, then the upper and lower bounds on the contribution of the lightweight elements to the entropy look like this function here, which is gamma, the weight of S times log n over gamma. And this suggests that in our strategy on the previous slide, we said that we're going to write the entropy as the sum of the contribution of the light and the heavy elements separately. So this suggests that we don't need to estimate the contribution of the lightweight elements to the entropy separately, but we do need to estimate it separately, but we don't need to know the weights of all the lightweight elements individually. We only need to know the net weight of all the lightweight elements. And this is an important part of how the algorithm works. So yeah, just to recap, the main results that we have are, in terms of upper bounds, are a quadratic improvement for the estimation of Shannon entropy. So to remind you, classical algorithms have a complexity that scales essentially as n to the 1 plus eta over gamma squared. And so we have a 2 in the denominator there, which expresses the quadratic speedup. And for von Neumann entropy, the complexity is n to the 1 over gamma squared, which is still sublinear. And it's interesting to note that there's a quadratic gap between the quantum query complexity of estimating Shannon and von Neumann entropies. And this fits in with a general pattern that we observe in algorithms that test properties of classical distributions versus analogous properties of quantum states. Okay, so the key ideas that go into our work to proving the upper bound are to apply the same thresholding idea that's used in the classical algorithm. So we first split up the domain into heavy and light elements, and we do this by using the quantum singular value estimation procedure. So quantum singular value estimation allows us to compare the probabilities, the underlying probabilities pi, and flag the subspaces that consist of heavy elements separately from the subspace of elements that consist of light elements. And after singular value estimation, we use this popular technique of singular value transformations in conjunction with an approximation of the log function, the logarithm, by power functions and polynomials. So one of the novelties is that we use an approximation that's good up to multiplicative precision for the logarithm. And we use quantum amplitude estimation, which is a standard procedure for eventually reading out what the algorithm computes. And the actual speed up for Shannon entropies, the quadratic speed up, comes from the ability to compute with square root of pi. And we'll see this in a couple of slides. And the sublinear complexity for von Neumann entropy depends on the fact that we're using the multiplicative approximation for the logarithm, and of course, the heavy light thresholding approach that is built into the classical estimator. Okay, so we already saw that we're going to use the quantum singular value transformations method. And this method has been quite popular in the last 3 years. It's the seminal work of Gillian et al. From 2019. So block encoding of a Hermitian matrix A is something that showed up in the literature nearly 10 years ago, nearly a decade ago, and essentially a larger unitary U that encodes a version of A, a subnormalized version of A, in its top left block. So in a sense, the 0, 0 subspace of the Hilbert space on which U acts is transformed according to A when U acts on a state in that Hilbert space. So we can extend this intuition and define what are called projected unitary encodings, where instead of having A in the top left block, we have A, in some sense, distributed or dispersed across the unitary in some subspaces that are flagged by projectors pi and pi tota. And we can even have approximate versions of A. We can define projected unitary encodings of approximate versions of A and still make use of these. So the key thing that works out for the purified access oracle is that for classical distributions, we know that the state is diagonal. So psi I is going to be the computational basis state I, and this allows us to construct a block encoding or a projected unitary encoding, which has singular values square root of pi. And this gives us operational access to these square roots in the sense that we can perform computations, we can manipulate these square roots, and this directly leads to the quadratic speedup. directly in conjunction with all the other techniques that go in. And it's a cornerstone of the speedup. For quantum density matrices, we don't know what the diagonal basis of the state is a priori. So we don't know psi a priori. And this is a bit of a roadblock. And we only know how to get operational access to either square root of pi over n or just the pi's themselves. For multiplicative estimation, we find in our work that the latter is more useful. And the former, square root of pi, an encoding that gives you access to the square roots of pi, has been used in previous work of Gillian and Lee to get additive estimates. So I think I'm getting close to the end of my presentation. And so singular value estimation, I'll just quickly mention that it's a subroutine that allows us to estimate the singular values of a block encoded matrix in superposition. And the complexity is essentially the same as that for amplitude estimation. So it scales as 1 over the position. And the algorithms are almost self-explanatory once you've seen the ideas. So we flag the subspaces of heavy and light elements by singular value estimation in the second step here. And the first part of the first branch of the state here encodes the net weight of all the lightweight elements. So we then read that out using quantum amplitude estimation with a carefully chosen precision. So that's how we estimate the weight of the lightweight elements. For the heavy elements, as I said before, we use a multiplicative approximation of the logarithm. So that's this function f of x that we use. And in particular, we construct it by using power functions. So using x to the plus or minus a in a certain combination, by choosing this parameter a that we can tune, proportional to log of the target precision over log of the inverse threshold, we can get a multiplicative approximation of the log function. So yeah, I won't go into the details of the estimation process for the heavy elements because that uses the more heavy machinery of the quantum singular value transformations procedure. So in step 3 here, we apply the singular value transformation, but in the end, we read out the estimate of the entropy of the heavy elements using quantum amplitude estimation. So to close the upper bound section, the entropy estimation procedure costs as much as the total cost for the light and heavy elements combined. And again, I won't go into the details because I'm running out of time. And I'll just mention that in the classical case, what's important is the sample complexity. And in the quantum case, the metric is the query complexity, but they're both information theoretic quantities. So we're not worried about computation, but we're worried about how many times we access the input. For lower bounds, the key ideas that we use are 2. So the first one is from work of Bellows in 2019 that I mentioned previously. He showed that for the promise problem of distinguishing 2 distributions P and P tilde in Hellinger distance, which is written here, the complexity is tightly characterized, and it's essentially 1 over the precision to which you want to distinguish the distributions. So we can reduce this problem of distinguishing 2 promised distributions to entropy estimation. And as a consequence, we get a lower bound of square root of log n for entropy estimation by quantum algorithms that work with any known quantum input model. And in particular, for the quantum samples model, this is the first non-trivial lower bound for any problem that we know of, because the quantum samples model can solve problems such as uniformity testing with trivial complexity. It can distinguish whether a distribution is uniform or epsilon far from uniform with 1 over epsilon complexity, whereas classically this costs square root of n. Okay, and for more on the lower bounds, I'd invite you to look at our paper. And by reducing the collision testing problem of Aronson and Hsieh to entropy estimation in the following way, so by constructing a pair of distributions that has a large ratio of entropies, we're able to show an n to the 1 over 3 gamma squared lower bound on quantum algorithms that estimate Shannon or von Neumann entropies. And this works for the purified quantum access model. So purified quantum query access model, which is, as I mentioned before, the most general model. Okay, so we obtain, as I said before, quadratic speedup for estimating Shannon entropies, sublinear algorithms for estimating von Neumann entropies. And the outlook from our work is looks fairly interesting. So, one of the outstanding questions is to tighten the lower bound that we obtain, because there is still a gap between n to the 1 over 3 gamma squared and n to the 1 over 2 gamma squared. And perhaps using the polynomial method is one way of doing this. And I think the techniques that we use here are fairly general and can be extended to the estimation of other functionals of distributions, such as Renyi entropies and divergences. Okay, so I think I'll stop here, and thanks for your attention.